Welcome to the fourth session of this integration series. In this session, we continue to demonstrate how to use various techniques to find integrals of trigonometric functions together with their inverse functions, exponential functions, as well as mixed forms of functions. In this session, 10 worked examples are illustrated.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the fourth session of this integration series. Here, example 1 is to find the integral of the fourth power of cosec x dx. Since the differentiation of cosec x equals negative cosec x cotangent x, negative cosec x cotangent x dx can be written to d cosec x. Since the differentiation of cotangent x equals negative cosec squared of x, negative cosec squared of x dx equals d cotangent x. Hence, the antiderivative is written to the integral of cosec squared of x times 1 plus cotangent squared of x, or in parentheses dx, which can be simplified to the integral of cosec squared of x dx plus the integral of cosec squared of x times cotangent squared of x dx, which is transformed to the integral of cosec squared of x dx minus the integral of cotangent squared of x d cotangent x, which equals negative cotangent x minus 1/3 times cotangent cubed of x plus c. Therefore, the antiderivative equals negative cotangent x minus 1/3 times cotangent cubed of x plus c. Example 2 is to find two antiderivatives with trigonometric functions. As for the first antiderivative, since sine 3x sine 2x can be transformed to 1/2 times cosine x minus cosine 5x, or in parentheses. Hence, the antiderivative is written to 1/2 times the integral of cos x minus cos 5x, or in parentheses dx, which equals 1/2 times sine x minus 1/10 times sine 5x plus c. As for the second antiderivative, since cos 2x can be transformed to 2 times cos squared of x minus 1, the antiderivative equals the integral of 2 cos x minus sec x, or in parentheses dx. Since the differentiation of ln of sec x plus tangent x equals sec x, the antiderivative equals 2 sine x minus ln of the modulus of sec x plus tangent x plus c. Example 3 is to find two antiderivatives. As for the first one, since the differentiation of tangent x equals the reciprocal of cos squared of x, the antiderivative equals the integral of tangent x d tangent x by dx, which can be written to the integral of tangent x d tangent x, which equals 1/2 times tangent squared of x plus c. As for the second antiderivative, since cos to the fourth of x minus sine to the fourth of x can be written to the sum of cos squared of x and sine squared of x times the difference of cos squared of x and sine squared of x, as shown on the screen, which equals cos squared of x minus sine squared of x, which is cos 2x. Therefore, the antiderivative equals the integral of cos 2x dx, which is 1 over 2 times sine 2x plus c. Example 4 is to find two antiderivatives with trigonometric functions as their integrands. As for the first antiderivative, since the differentiation of sine x plus 1 is cos x, which gives d sine x plus 1 equals cos x dx. Hence, the antiderivative is written to the integral of cos x times the square root of 1 plus sine x dx, which also can be written to the integral of the square root of 1 plus sine x d 1 plus sine x, all in parentheses, which equals 2 over 3 times 1 plus sine x, all in parentheses, raised to the 3 over 2 plus c. As for the second antiderivative, since 1 plus sine x can be transformed to sine x over 2 plus cos x over 2, all in parentheses, squared, the antiderivative equals the integral of sine x over 2 plus cos x over 2, all in parentheses, dx, which can be written to 2 times the integral of sine x over 2 dx over 2 plus 2 times the integral of cos x over 2 dx over 2, which is 2 sine x over 2 minus 2 cos x over 2 plus c. Example 5 is to find an antiderivative with trigonometric functions as its integrand. Since the integrand can be transformed and simplified to cos x plus sine x, all in parentheses, cubed, over the result of 2 sine x cos x plus sine squared of x plus cos squared of x, which is cos x plus sine x. Hence, the antiderivative is written to the integral of cos x plus sine x, all in parentheses, dx, which equals sine x minus cos x plus c. Example 6 is to find an antiderivative of sine mx sine nx dx, where both m and n are positive integers and m does not equal to n. Since sine mx sine nx can be transformed to its addition form, so it equals 1 over time times cos of mx minus nx minus cos of mx plus nx, all in parentheses. Hence, the antiderivative equals 1 over 2 times the integral of cos of mx minus nx minus cos of mx plus nx, all in parentheses, dx, which equals the reciprocal of 2m minus n, all in parentheses, times sine of mx minus nx minus the reciprocal of 2m plus n, all in parentheses, times sine of mx plus nx plus c. Here, example 7 is to find two antiderivatives. As it can be seen on the screen, in the first antiderivative, after the function is simplified by taking and cancelling the common factor from both numerator and denominator, it is decomposed to e to the x over e to the x minus 1 plus 1 over e to the x minus 1. Hence, the antiderivative can be written to the integral of e to the x over e to the x minus 1 dx plus the integral of 1 over e to the x minus 1 dx. The second term, however, can be further separated to 1 over e to the x minus 1 minus 1 over e to the x. So the antiderivative equals ln of the modulus of e to the x minus 1 plus ln of the modulus of e to the x minus 1 minus ln of e to the x plus c, which can be simplified to 2 times ln of modulus e to the x minus 1 minus x plus c. As for the second antiderivative, since the differentiation of x plus 2 or in parentheses squared plus 9 equals 2 times x plus 2 or in parentheses, the integrand function is transformed by adding and subtracting 8 in the denominator and then decomposed into 2 fractions. Hence, the antiderivative is written to the integral of 2 over the sum of x plus 2 or in parentheses squared plus 9 dx plus 2 or in parentheses squared plus 9 minus 8 over the sum of x plus 2 or in parentheses squared plus 9 dx plus 2 or in parentheses, which equals 2 times ln of x squared plus 4x plus 13 or in parentheses minus 8 over 3 arctangent open bracket x plus 2 all over 3 close bracket plus c. Example 8 is to find two antiderivatives. As for the first one, the integrand function can be decomposed using partial fraction technique. Hence, the antiderivative is written to the integral of e to the 2x over the sum of e to the 2x plus 1 dx plus the integral of e to the x over the sum of e to the 2x plus 1 dx, which can be written to half of the integral of 1 over e to the 2x plus 1 d e to the 2x plus the integral of 1 over e to the x squared plus 1 d e to the x, which equals 1 over 2 times ln e to the 2x plus 1 or in parentheses plus arctangent of e to the x plus c. As for the second antiderivative, since the numerator of the integrand function can be simplified by grouping the term of x squared plus 2, it becomes x squared plus 2 or in parentheses squared minus 4 times x squared plus 2 or in parentheses plus 5. Apart from completing square technique I used here, you may achieve this by doing the long division. Okay, the integrand is now simplified to x squared minus 2 plus 5 over the sum of x squared plus 2. Hence, the antiderivative is written to the integral of x squared minus 2 plus 5 over the sum of x squared plus 2 or in parentheses dx, which equals 1/3 of x cubed minus 2x plus arctangent of x over square root 2 plus c. Here example 9 is to find two antiderivatives. As for the first one, we let u equals x squared, which gives du equals 2x dx. Hence, the antiderivative is written to half of the integral u squared over the sum of u squared and 2 du, which equals half of the integral of 1 minus 2 over the sum of u plus 2 or in parentheses du, which equals u over 2 minus ln of the sum of u and 2 plus c. After substituting back to the variable x, the antiderivative equals x squared over 2 minus ln of open bracket x squared plus 2 close bracket plus c. As for the second antiderivative, since the differentiation of sine x is cos x, so cos x dx can be expressed to d sine x. Hence, the antiderivative is written to the integral of 2 times sine x plus 1, or in parentheses over the product of sine x plus 3, or in parentheses, and sine x minus 1, or in parentheses d sine x, which equals the integral of the sum of the reciprocal of sine x plus 3 and the reciprocal of sine x minus 1, or in parentheses d sine x, which equals ln of sine x plus 3, or in parentheses, plus ln of 1 minus sine x, or in parentheses, plus c. Here, example 10 has two antiderivatives. As for the first one, since the differentiation of sine x is cos x, which gives cos x dx equals d sine x. Hence, the antiderivative is written to the integral of the reciprocal of the product of sine x minus 1, or in parentheses, and sine x minus 2, or in parentheses d sine x, which equals ln of the modulus of sine x minus 2 subtracted by ln of the modulus of sine x minus 1 plus c, which can be simplified to ln of the modulus of the quotient of sine x minus 2, or to the result of sine x minus 1, then plus a constant c. As for the second antiderivative, since the integrand function can be simplified to 8 over e squared times 1 minus the reciprocal of the sum of 1 and e squared times x, or in parentheses, the antiderivative can be written to 8 over e squared of the integral of 1 minus the reciprocal of the sum of 1 and e squared times x, or in parentheses dx, which equals 8 over e squared times x minus ln of the modulus of 1 plus e squared times x over e squared, or in parentheses plus c, which can be further simplified to 8x over e squared minus 8 over e to the fourth times ln of the modulus of 1 plus e squared plus c. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.